Hi everyone. Today's lesson is going to be about molar dilutions, how we can dilute solutions that we know the molarity of. So the first question is, why would we want to do that? Why don't we just always start with pure solute? Well, sometimes it's just not practical. Some solutes are dangerous to keep around or are very unstable. Some solutes start off as gases. It's just not practical for me to try to dissolve a gas in the lab before you guys come in. Acids typically are gases in their natural state. It's just not practical for me to hold gas canisters of hydrogen chloride in my back room. And so instead what I do is I order from the scientific company. They mix it up and I order a really, really concentrated hydrochloric acid solution. And then I'm able to water that down into whatever concentration that you guys need. First rule that we need to know then is you can only go down, right? The only thing we're going to add here is water. I'm not going to add hydrogen chloride when I dilute the solution. The only thing I'm going to add is water. So we can't make anything ever more concentrated than what we call it a stock solution. That original solution that I purchased is called a stock solution. It sits in my stock room and it contains all the stuff I need. So the way it basically works is we start off with this really concentrated solution, but we only have a little tiny bit of it, and I have this much here, and I fill it up with water, and I end up with a less concentrated solution. But you'll notice that the original the original solution here kind of ends up over here. The number of moles of solute that I started with is the number of moles of solute that I'm going to end with. I don't lose moles of solute from where my concentrated was over here to my less concentrated. So the moles of solute in this solution and the moles of solute in this solution will be the same. So if we look back at that equation that we've been working with the last couple of days, where the molarity of the solution equals the number of moles over the volume, like that, and we solved this equation for number of moles, right? We talked about this before about how we're going to cross multiply, right? So we would take the m times the v and then n times 1, and I end up with a number of moles is equal to the molarity of the solution times the volume. Well, again, the number of moles in here is going to be the same as the number of moles in there, which means that the molarity and the volume of the concentrated will equal the molarity times the volume of the diluted solution, like that. And this is right here is the equation we're going to use to solve for these things. Okay, the molarity of the concentrated solution times the volume of the concentrated solution will equal the molarity of the dilute times the volume of the dilute. So how do we use that? Well, let's say that I have a 12 molar stock solution, okay, and I know that I want to make, say, a 500 milliliters of 0.3 molar. We'll write that down. Okay. Well, I know right now the molarity of the stock solution is always the concentrated again. I know the volume that I want to make of the dilute solution, and I know the concentration that I want of the dilute solution. All I have left is the volume of the concentrated solution, and honestly, that is all you will ever have left. That is the only thing we can ever really be looking for. Okay. Anything else, it just doesn't make sense. We would know what our concentrated solution, so we'll label these things C, this is B, D, this is molarity dilute, C equals. So, like a good girl, I write down what I know in my equation. I'm working on that, right? And then we're going to fill in the values that we have. So the concentrated solution is 12 molar times my volume is equal to 0.3 molar times, now let's talk about this for a second. I'm going to put this 500 in here, and I want to show you where this goes. Not the 500. We'll convert it to liters like we always have, 0.5 liters. Okay, and so I would take 0.3 times 0.5, okay, and then I'm going to divide that by 12, I don't have a calculator over here, so 15 divided by 12. I can do this. I'm gonna go get a calculator. I'll be right there. Yoink. Okay, so clear. Try this again. 0.3 times 0.5 divided by 12. I'm going to get 0.0125. Okay, and I ran out of room, so VC equals 0.0125. That's in liters, right? Well, that's not very practical. I really don't have devices that measure in liters that small, so I'd have to go to milliliters anyway. So we'd move it over 3 spaces, 1, 2, 3, and we get 12.5 milliliters, right? Well, it just kind of seems silly. I had to convert this one to liters, and then I have to convert this one back to milliliters. Well, what would happen if we just didn't convert this one to liters in the first place? What if I just left it as 500 milliliters? I'm not going to push it into the calculator because I know what does happen. Okay, but if you want to go try it and see that I'm right, if you take 500 times 0.3 divided by 12, you're going to get 12 and a half. The reason this works is when I take the molarity times the milliliters, remember this molarity? We use moles per liter. We're going to change it to moles over liters. Well, the reason we usually have to have our volume in liters is so that the liters that are on the bottom here and the liters here cancel out. Well, they don't quite cancel here. What I actually end up with is millimoles. And when I take moles over liters times milliliters, I end up with millimoles. But as long as I accept that I'm going to have millimoles on this side too, it doesn't really make a difference. It's a proportion this time. And so as long as I put milliliters in here, I'm going to get milliliters out on this side. So as long as they're the same, it's okay. And as long as we know that, then we can maintain that same unit and we don't have to change our milliliters into liters. But otherwise, they really are that easy. And once again, there's the equation. All you have to do is plug in the values that you'll have and find the one you don't have. And I can pretty much promise you that the volume of the concentrated here is going to be what you're looking for absolutely every time. So now final question, how do we actually make this solution? Well, you'll remember back from our safety days that, no mask on, I can lick my fingers. Remember back from our safety days that when diluting acids, we add acid to water is doing what you order. So what we don't do is to put that 12.5 milliliters of very, very concentrated acid into a volumetric flask and start pouring water on top of it. So instead, what we're going to do is we're going to take our volumetric flask and we're going to put some water in it first because we need to add acid to some water. You'd probably fill it about halfway full because we know that we're only going to put just a little bit of that acid in. So you'll probably fill your volumetric flask about halfway filled with water, then add the 12.5 milliliters of acid, swirl it around until it's all dissolved so that the heat will dissipate. Well, now it's mostly pretty dilute anyway, and adding water on top of dilute acid is really not a problem. So we would add water, fill that up to the top, to the line, stopper it, and shake it up. Okay? All right. Thank you very much. We'll see you next time after I figure out how to push this.